Ukraine just unveiled a weapon that, according to every conventional defense analyst, should not exist for at least another decade. Not a prototype, not a concept gathering dust in a Pentagon research lab. A fully functional directed energy system that has already been deployed, tested in combat conditions, and is now actively hunting Russian aircraft over Ukrainian skies. Russia's defense ministry has gone silent on the matter. That silence tells you everything you need to know. By the time we're done here, you'll understand exactly why Moscow is more terrified of this single weapon system than they are of the entire combined arsenal of NATO tanks, missiles, and fighter jets that have poured into Ukraine over the past 4 years. Welcome to States News. If this is your first time watching, hit subscribe and turn on notifications, because what I'm about to show you represents the single most significant leap in battlefield technology since the introduction of precision-guided munitions in the 1991 Gulf War. This isn't just another Ukrainian innovation story. This is a fundamental disruption of how modern warfare operates. I'm going to walk you through exactly what Ukraine has deployed, how they developed a weapons system that should have required billions in research funding and decades of technological advancement, and why this changes the strategic calculus, not just for the war in Ukraine, but for every major military power on Earth. We'll examine the technical specifications of this directed energy weapon, the tactical advantages it provides against Russia's current doctrine, the strategic implications for air superiority in modern conflict, and the geopolitical consequences that are already rippling through defense establishments from Beijing to Washington. By the end, you'll understand why this single development has the potential to render obsolete hundreds of billions of dollars worth of existing air defense infrastructure, and why Russia's leadership is privately discussing scenarios they never thought they'd have to confront. Before we dive into what Ukraine has actually built, we need to understand why directed energy weapons have been the holy grail of military technology for the past 40 years, and why every major power has failed to field an effective system despite pouring astronomical sums into research. Directed energy weapons, specifically high-energy lasers designed for air defense, represent a theoretical perfect solution to one of warfare's most persistent problems. Traditional air defense relies on kinetic interceptors, missiles that must physically strike incoming threats. Each interceptor costs anywhere from $50,000 for basic systems to $4 million for advanced missiles like the Patriot PAC-3. You fire one missile to destroy one drone. The economics are brutal. When your adversary can build crude Iranian Shahed drones for $20,000 each and launch them in swarms of 50, you're spending $10 million in interceptors to stop $1 million worth of threats. The defender goes bankrupt before the attacker runs out of drones. Lasers change that equation completely. Once the system is built, each shot costs essentially nothing. A few dollars of electricity to power the beam. No multi-million-dollar missiles consumed with every engagement. You can shoot down drone after drone, missile after missile, aircraft after aircraft, limited only by your power supply and the system's ability to manage heat buildup. It's the defensive equivalent of unlimited ammunition. That's the theory. The reality has been far more complicated. The United States has been developing high-energy laser systems since the 1980s. The airborne laser program spent $5 billion trying to mount a megawatt-class chemical laser on a Boeing 747 to shoot down ballistic missiles. It technically worked in controlled tests, but proved completely impractical for real operations. The Navy's laser weapon system demonstrated drone kills in 2014, but never progressed beyond limited trials. The Army's IFPC HEL program has been promising imminent deployment for the past 6 years. Israel's Iron Beam has been 2 years away from operational status for the last decade. The fundamental challenges are power generation, thermal management, and atmospheric interference. You need enormous amounts of electrical power to generate a beam strong enough to destroy hardened targets at tactically useful ranges. That power generation creates massive heat that must be dissipated or the system destroys itself. Even with sufficient power, atmospheric conditions, dust, fog, rain, or smoke scatter the beam and reduce effectiveness. These aren't minor engineering challenges. They're fundamental physics problems that have stumped the world's most advanced defense contractors despite budgets that dwarf the entire Ukrainian defense industry, which makes what Ukraine has accomplished genuinely shocking. According to multiple confirmations from Ukrainian defense sources reported by Defense Express and Euromaidan Press, Ukraine has not only developed a functional high-energy laser air defense system, but has deployed it operationally and achieved confirmed kills against Russian drones and potentially crewed aircraft. The system is designated Trizub, the Ukrainian word for trident, their national symbol. Unlike Western programs that have languished in development hell for decades, Trizub went from concept to combat deployment in under 18 months. Let me be very clear about what we're discussing. This is not the small-scale laser pointer systems Ukraine demonstrated last year. Those were low-power systems effective against small commercial drones at ranges of a few hundred meters. Trizub is a different category entirely. According to technical analysis published by Militarnia, the system operates in the 100-kilowatt power class, comparable to the most advanced systems under development by the United States. It's mounted on a mobile platform, providing the tactical flexibility that fixed installations lack. And it has demonstrated effective engagement ranges exceeding 5 kilometers against aerial targets, confirmed through multiple documented intercepts over Kyiv and Dnipro regions. Now here's where the story becomes genuinely fascinating. How did Ukraine, a nation with a defense budget a fraction of what the Pentagon spends on coffee, develop a weapons system that has eluded American, Israeli, British, and Chinese defense establishments despite their virtually unlimited resources? The answer reveals something profound about how modern warfare drives innovation in ways that peacetime development never can. Ukraine didn't start with a clean sheet design and decades to refine it. They started with an immediate existential threat. Russia was launching Shahed drone swarms nightly, overwhelming Ukrainian air defenses through sheer numbers. Every interceptor missile fired was one less available for the next wave. The economics were unsustainable. Ukrainian engineers weren't working toward a theoretical future capability. They were solving a problem that was killing their citizens every single night. That pressure created a development environment radically different from Western defense acquisition. There was no time for lengthy requirement studies, competitive bidding processes, or risk-averse bureaucratic review. Ukrainian engineers, many of them veterans of the country's thriving tech sector, were empowered to iterate rapidly, test aggressively, and fail forward in ways that would be impossible in traditional defense programs. According to reporting by Kyiv Post, the Trizub program involved direct collaboration between military personnel experiencing the drone threat firsthand and civilian engineers developing solutions in near real time. They also benefited from something Western programs don't have: immediate access to the actual threat systems they needed to defeat. Ukraine has captured dozens of intact Shahed drones. They know exactly what materials these drones are constructed from, precisely how much energy is required to disable their guidance systems or ignite their fuel, and the specific vulnerabilities in their design. Western programs test against simulated threats or best-guess replicas. Ukraine tested against the actual weapons Russia was using. But the technological breakthrough goes deeper than rapid development timelines. According to technical analysis, Ukraine appears to have solved the thermal management problem through a hybrid architecture that Western programs haven't pursued. Instead of trying to generate all the beam energy from a single massive laser assembly, Trizub uses a distributed array of smaller, more manageable laser modules. Each individual module generates a fraction of the total power, making thermal management far simpler. The beams are then combined through precision targeting optics to create the concentrated energy needed to destroy targets. This approach sacrifices some theoretical efficiency, but gains massive practical advantages. Smaller modules are easier to manufacture, simpler to maintain, and cheaper to replace if damaged. The distributed architecture provides redundancy. If one module fails, the system continues operating at reduced capacity, rather than going offline completely. It's an elegant solution born from engineering constraints rather than pursuit of theoretical perfection. The tactical implications of this system are already visible in Russian operational behavior. According to Ukrainian military intelligence statements reported by Ukrainian Pravda, Russian drone operations over Ukrainian-controlled territory have shifted noticeably in recent weeks. Shahed strikes, which previously came in concentrated swarms designed to overwhelm air defenses through saturation, are now arriving in smaller, more dispersed packages. Russian operators are avoiding predictable flight paths and concentrating on low-altitude approaches where atmospheric interference might degrade laser effectiveness. This behavioral shift is significant. It means Russia recognizes the threat and is adapting tactics specifically to counter it. That adaptation comes with costs. Smaller, dispersed drone packages are less effective at overwhelming defenses, but also less effective at achieving concentrated damage against high-value targets. Low-altitude flight paths reduce laser effectiveness, but also reduce the drone's own sensor range and expose them to shorter-range air defenses and even small arms fire. Russia is being forced into tactical compromises that reduce the overall effectiveness of their drone campaign. But the implications extend far beyond Ukrainian battlespace. Every major military power is watching this development with intense interest and growing concern. The strategic calculus that has governed air power for the past 70 years is suddenly in question. Modern air warfare is built on a fundamental truth. Aircraft are expensive and difficult to replace, while air defense missiles are cheaper and easier to produce. An F-35 costs $80 million. A surface-to-air missile costs a few million at most. This economic relationship means that in any extended conflict, The attacker with limited aircraft eventually loses the attrition battle to the defender with deep missile inventories. That's why air superiority campaigns begin with suppression of enemy air defenses. You must destroy the defender's missile systems before committing your expensive aircraft to sustained operations. Directed energy weapons flip this equation. Now the defender has unlimited magazines. The attacker's expensive aircraft face a defensive system that never runs out of ammunition, never needs resupply convoys, and costs almost nothing per shot. The entire doctrine of suppression of enemy air defenses must be reconsidered. How do you suppress a defensive system that you can't deplete through sustained operations? China is undoubtedly analyzing this question with particular intensity. Chinese military doctrine for a Taiwan scenario depends heavily on achieving air superiority through overwhelming initial strikes followed by sustained air operations to prevent American intervention. Those plans assume Chinese aircraft and missiles can attenuate Taiwanese air defenses through sheer volume of attacks. If Taiwan deploys effective directed energy systems, that assumption collapses. The air superiority timeline extends indefinitely. The window for successful amphibious operations might never open. Russia faces even more immediate concerns. Their entire air campaign over Ukraine has been predicated on standoff strikes using cruise missiles and long-range drones, keeping aircraft outside the range of Ukrainian air defenses. This approach works when the defender has limited interceptors and must prioritize targets carefully. It fails catastrophically when the defender can engage every threat without worrying about ammunition expenditure. Russia's cruise missile inventory, built up over decades and already significantly depleted, becomes vulnerable to a defensive system that can shoot indefinitely. The second-order effects ripple through global defense economics. Every nation currently investing billions in advanced fighter aircraft must now consider whether those aircraft can survive in an environment where directed energy air defense is proliferating. The F-35 program, the most expensive weapon system in human history, at over $1.7 trillion in lifetime costs, is built on assumptions about air defense capabilities that may no longer hold. If relatively small nations can deploy effective laser systems that threaten advanced stealth aircraft, the entire economic logic of fifth-generation fighter programs comes into question. Now let's address the complications and limitations, because they are substantial, and ignoring them would be dishonest analysis. First, we have very limited technical data on Trizub's actual performance envelope. Ukrainian defense officials have strong incentive to exaggerate capabilities to influence Russian planning and boost domestic morale. The confirmed intercepts we know about involve drones, relatively soft targets with minimal hardening against laser attack. We don't have verified evidence of intercepts against hardened cruise missiles, ballistic missiles, or crewed aircraft with defensive countermeasures. The claim that Trizub can engage manned Russian aircraft remains unverified and should be treated with appropriate skepticism until supporting evidence emerges. Second, directed energy weapons remain fundamentally vulnerable to atmospheric conditions. Physics doesn't care about engineering cleverness. Dense fog, heavy rain, or battlefield smoke will degrade or completely negate laser effectiveness. A competent adversary can exploit weather conditions or create artificial obscurance to reduce the threat. Ukraine's system works in the specific environmental conditions of Ukrainian airspace. Those conditions don't exist everywhere, which limits how revolutionary this technology can be globally. Third, there are hard limits on engagement range that kinetic systems don't face. A missile can travel dozens or hundreds of kilometers to intercept a threat. A laser is fundamentally constrained by line of sight and atmospheric absorption. Beyond certain ranges, even the most powerful laser becomes ineffective. This means laser systems excel at point defense, but can't replace long-range interceptors for many scenarios. They're not a comprehensive solution to air defense, they're one layer in a multi-layered defense architecture. Fourth, the system still requires substantial electrical power. Ukraine's power grid has been under sustained Russian attack for 4 years. Operating high-energy lasers requires reliable electricity generation and distribution. In scenarios where the defender's infrastructure is degraded, the theoretical advantage of unlimited ammunition becomes meaningless if you can't generate the power to fire. Russia surely recognizes this vulnerability and will intensify attacks on Ukrainian power infrastructure, specifically to neutralize this capability. Finally, we must acknowledge that if Ukraine developed this system in 18 months, other nations with greater resources can match or exceed this capability in similar timeframes. The technological breakthrough isn't a permanent advantage. It's a temporary edge that will inevitably be replicated. Russia is certainly pursuing crash programs to develop equivalent systems right now. The question is whether Ukraine can exploit this advantage during the window before countermeasures and equivalent systems proliferate. So what does this actually mean for the trajectory of the war and for global military competition more broadly? In the immediate term, Ukraine has achieved something that extends beyond the tactical capabilities of the weapon itself. They've demonstrated that rapid, necessity-driven innovation can match or exceed what traditional defense establishments produce, despite unlimited budgets and decades of development time. That demonstration effect matters enormously. It will reshape how nations approach defense acquisition and how much credibility they assign to lengthy development timelines for advanced systems. For the war in Ukraine specifically, Trizub provides partial solution to the sustained drone and missile campaign that has been degrading Ukrainian infrastructure and civilian morale. It's not a complete solution, but it represents a qualitative improvement in defensive capability at precisely the moment when Ukraine's interceptor missile stocks were becoming critically constrained. The psychological impact on Russian planning may prove as significant as the tactical impact on intercept rates. For global military competition, this marks an inflection point. Directed energy weapons have transitioned from perpetual future technology to deployed operational reality. That transition will accelerate investment and development programs worldwide. Within 5 years, we should expect multiple nations to field competing systems. Within 10 years, directed energy air defense will likely be standard equipment for any serious military force. The nation that most effectively integrates these systems into operational doctrine, develops countermeasures and countermeasures, and adapts their broader military strategy to account for this new defensive capability will gain substantial advantage. That race is beginning right now, and Ukraine just took a commanding early lead. What we're watching unfold is larger than one weapon system or one conflict. We're seeing the emergence of a new paradigm in military technology development. The old model, where wealthy nations spent decades developing theoretical capabilities in peacetime laboratories, is being challenged by a new model where nations under existential threat innovate at emergency pace and deploy imperfect but functional systems immediately. Ukraine has just provided the proof of concept for that new model. Watch what happens next. Watch how quickly other nations move to replicate or counter this capability. Watch whether Western defense establishments accelerate their own programs or continue insisting that proper development requires another decade of refinement. Watch whether Russia can adapt their air campaign doctrine fast enough to mitigate this threat before it fundamentally alters the strategic balance. And watch this channel because we're tracking all of it in real time. If this analysis helped you understand why a weapon that shouldn't exist yet is already changing the calculus of modern warfare, subscribe and turn on notifications. We're covering the proliferation of directed energy systems and the race to develop effective countermeasures in upcoming videos. The future of air warfare is being written right now over Ukrainian skies, and you're not going to want to miss what comes next.